Welcome for this second module, third session. Second module, as we all know that is the gas turbine cycle. In that gas turbine cycle, Joule cycle, Bryton cycle, and then the optimum pressure ratio for the maximum work done. All the derivations we are discussed in the session 2. In the session 3, we are going to discuss this methods of improving the work output. Work output, as we all know that the work output is nothing but the directly proportional to the thermal efficiency of the Bryton cycle. Here, the thermal efficiency of the Bryton cycle uh, depends on the work output. See, thermal efficiency of the any cycle is equal to the work done by heat supply. Thermal efficiency and the work done both are directly proportional. Hence, the work done increases, thermal efficiency also increases. There are three methods of improving the work output in the of the Bryton cycle. That is, the thermal efficiency can be improved by three methods. First method is the regeneration. Regeneration is nothing but the utilization of heat present in the exhaust gases. Means it is a waste heat recovery system. The heat which is going out through the exhaust as and when the the cycle operates, the exhaust will be having a lot of temperature in that. Means heat will be in that. The in the regeneration, the waste heat is recovered and then preheated of uh, the air which is fed to the compressor. And then intercooling. Next method is intercooling. The cooling the air compressed in the first stage to the initial temperature before it is sent to the second stage of compressor. Means always in the multi-staging intercooling will be applied. For the single the compressor there is a intercooling is not possible. But only the thing is there should be the two compressor. In between that there is an intercooler will be there. Means the compressing in the one stage requires the maximum work which is work which is developed in the turbine, which is utilized for the compressor for the compression purpose. If you use only one stage compressor, then maximum work will be utilized. Maximum work will be absorbed, and then the work absorption can be reduced by using this intercooler. That method is called as intercooling. In this method, the reduces the work input to the compressor, so that compressor is a work absorbing equipment. And then reheating, another method of improving the thermal efficiency or the work output of the Bryton cycle is the reheating method. Heating the air, heating the air expanded in the first stage of the turbine to the initial stage. After expansion in the first stage of the turbine, it loses its temperature and pressure due to by means of doing some work. Some mechanical work will be work output will be there from the turbine. After that, once again, if you heat that the exhaust of the first stage to the initial stage, and then it is fed to the second stage of the turbine, so that there is a work output is going to increase. Meanwhile, the efficiency also increases. Let us discuss the one by one of the methods of improving this thermal efficiency. That is the regeneration, as I said in the first stage. Here you can observe there is the open cycle. This one is the compressor. This compressor is and the turbine both are coupled to the single shaft. Whatever the turbine which is developing some work, some part of the work is first it is absorbed by the compressor which is incorporated within the cycle. So hence the compressor will be working and then compresses the air. Air from the atmosphere is sucked by the compressor and then it is compressed, and then after that it is passed through this regenerator, and then it is a combustion chamber. See, it is a heat exchanger is nothing but the regenerator is the heat exchanger. Heat exchanger you are going to study in the heat and mass transfer subject in the sixth semester. But here, the in the simple manner, I will tell you this: the what is heat exchanger? Heat is exchange takes place between the from 6 to 2. These are the you consider this as a pipe, and then this is also one of the pipe. Both are enclosed in the one container. There's a closed container, the which is having more heat, and then so that the heat will be given to this line, this pipeline. Okay, small pipelines which are the insulated pipelines, so that the heat which is passing through this uh, the 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 incoming line, yes, the heat exchange between the hot gases through passing through this line 4 to 6 to the 2 to 5, means the heat transfer takes place between the hotter fluid to the colder fluid. That is a heat exchanger. Okay, the regenerator is one of the type of heat exchanger. There the heat exchange between the exhaust gases to the inlet uh, the gases. Okay, see here the heat is taken from this exhaust gases, and then it is fed to the combustion chamber. In the combustion chamber, fuel will be supplied, hence the burning takes place, so that uh, there is a increase in the temperature and pressure. Like any other the heat supply, here also the heat is going to supply it, or fuel is directly burnt in the combustion chamber, so that pressure and temperature is going to increase. After that, it is again it is sent to the turbine or fed to the turbine. Like like any other circuits, here also the turbine and compressor are working in the same manner, but only the thing is, after feeding the turbine, there's a some work will be developed in the turbine, means by expanding the gases, some work is going to develop. After developing the some work, the exhaust is going through the exhaust gases going to the atmosphere, instead of using this regenerator, as the exhaust going out to the atmosphere, then there is no use of this the use or utilization of this the heat which is going to the atmosphere is a waste one. And if you utilize that heat, then only the efficiency, the work output can be improved in this the circuit. In this circuit means Bryton cycle. Bryton cycle, gas turbine cycle. That is, a Bryton cycle is nothing but the gas turbine cycle. So whatever the exhaust which is going to the atmosphere, instead of that leaving as it is, if we pass that to the through the heat exchanger, heat exchanger means this regenerator here, particularly we are calling this as a heat regenerator. Regenerator means, instead of eating the incoming air, but it is the heat is supplied from the exhaust. That is a regenerator. The heat exhaust gas heat is going through this the regenerator, hence the heat exchange takes place. This is the example I'll give you. The compressor is absorbing the atmospheric air. Atmospheric air usually 35 degree, 30 degree, within 40 degree will be there. 30 to 40 degree will be there. Optimum temperature. Pressure always, as we all know, that 1.013 bar. 13 bar is nothing but a 10 to the power of 5 Newton per meter square, 10 to the power of 5 pascals. That is the standard value, as you all know that now from the beginning of this applied thermodynamics. Here, that pressure and the temperature, atmospheric temperature air is entering. Instead of regenerator, if you fed directly the combustion chamber, first whatever the fuel is supplied, it has to heat the atmospheric air to the maximum level. Starting from 35 degree, it is heating, means it requires around some fuel. Instead of the directly feeding, if there is the regenerator is incorporated, then the heat, whatever the atmospheric air is there, it is heated priorly. It is priorly to the combustion chamber, so that the heated this incoming air is heated up to the 70 degree. Example, okay, 70 degree, 75 degree, whatever. For example, I will tell you 35 to 75 degree, whatever the fuel is supplied, that fuel is supplied. Instead of supplying the fuel from the 35 degree, it is supplied from the 70 degree. Means that much of the fuel you are supplied, you are going to reduce. That is the main intention of this using the regenerator in the Bryton cycle. That's why the work development work developed will be increases. Okay, thermal efficiency increases. In the TS diagram, particularly in the TS diagram, as you all know that 1 to 2, 3 to 4, 4 to 1 is the 4 to 1 is the closed cycle, the Bryton cycle, closed Bryton cycle. This all processes are reversible, and then the heat is supplied. See here, okay, 1 to 2. Let us tell the one more. Let us discuss this the different process. 1 to 2 is the isentropic because entropy is same. Isentropic process. 2 to 3 is the constant pressure heat addition, and then the 3 to 4 is again the isentropic. 4 to 1 is the constant pressure heat rejection process. As you all know that. 2 to 3. I am concentrating this. 2 to 3 is the heat addition process. Instead of supplying the heat from the 2, if you supply 5, optimum. If you supply 5, this much of heat supply is reduces because thermal efficiency is equal to work done by heat supply. If the heat supply reduces, then automatically thermal efficiency increases, right? Like that, if it is the exhaust 3 to 4 is this is nothing but the isentropic work done process. 3 to 4 is the isentropic expansion or the work done process. Here, turbine is going to develop some work. After it's a turbine inlet and turbine outlet. Let us go for the previous diagram slide. You see 3 to 4, 1 to 2 is the isentropic compression, 2 to 3 is the heat addition process, 3 to 4 is the expansion process, 4 to 1, again 4 to 1 is the including this the regenerator. 4 to 1 is the heat rejection process. Okay, here. See, instead of that, whatever the exhaust of the turbine is equivalent to the preheating, then it is called as ideal regeneration. This is called as ideal regeneration. If it is optimum, maybe ideal it is not possible because of the lot of losses will be there in the circuits or cycles. Maybe the frictional loss, maybe the pressure loss, maybe lot of losses will be there. Due to that losses, optimum at 5 it is entering from the regenerator. At 5 from the regenerator heat will be supplied this much. 2 to 3 is the your actual saving of the heat supply. Okay, this is only the 5. From 5 you are supplying. This is the regeneration. Okay. The regeneration efficiency, effectiveness, the regenerator effectiveness is nothing but the 5 dash minus 2. 5 dash minus 2 divided by 5. If 5 is greater than 4, 5 is greater than 4, it is called as 4 minus 2, T2. Okay. T4 minus T2, right? And one more important another method of the regenerator is the method of improving the thermal efficiency of the Bryton cycle is the intercooling. Intercooling, as I said, if you want to incorporate the intercooler, there should be the 2 stage of compressors. It is not possible to include the 1 stage. Compressor 1 and compressors 2. 2 compressors are there. In between that, there is a intercooler. Okay. In between that, there is a intercooler. There is a intercooler. See, our TS diagram I am included here itself. See here, there is a 2 stage of intercooler. There is a middle intermittent pressure P1 and P2 P2 and P4 is the different pressures. You see here 1 to 2 is the first stage isentropic compression process. 2 to 3 is again 2 to 3 in the intercooler, again it is a expansion process. And then 3 to 4 is the uh, isentropic compression process in the second stage. 4 to 5 it is a compression process, the constant pressure and the heat addition process. Okay, 5 to 6 5 to 6 is the again it is a expansion process, isentropic expansion process. 6 to 1, if you join this 6 to 1, again 6 to 1 it is a heat rejection process. If you include this the evaporator or the heat exchanger here, you will get the one more equipment here. Open cycle he has taken 6 to 1. See these dotted lines as you 1 to 2 dash and then 3 to 4 dash, it is actual cycle due to some losses. The actual compression, ideal compression, this one is actual compression. This the dark line is the ideal compression, this dotted line is the actual compression. Because of the losses, it is going lesser work done. Lesser work done means this area reduces. Area reduces means work done decreases. Area increases means work done increases. Okay. Area of the TS diagram is nothing but the work done, thermal efficiency. For that, this intermittent pressure is calculated like this. The Pi is equal to root of P1 by P2. This is the perfect intercooling. Another one is reheating. This is also one of the method of improving the Bryton cycle efficiency. Here, in the previous case, we are used the two compressors because intercooler there is a two compressors. We are cooling after this compressor. We are cooling the exhaust of the first compressor. Again, we are feeding. In the reheating, you see here, there is only one compressor, combustion chamber. After that, there are two turbines, turbine 1 and turbine 2, HP turbine or LP turbine, whatever you call it. Or else there is a one turbine in between, in the same turbine there is a two compartments. One is a HP turbine and the LP turbine. For the clarity, have made the two sections of this turbine. But in the actually all the textbooks and all the authors are writing like this only for showing these reheaters. Okay, reheaters. See, turbine 1 and turbine 2. In between that reheaters. See, after in simple words, I will tell you this air is compressed in the compressor, and then after compression, the pressure and temperature is going to increase. As the pressure and temperature increases, it is fed to the combustion chamber. Then there is a fuel is supplied. After the fuel supply, it is sent to the first stage of the turbine, first turbine. There the expansion takes place. It can be producing some work output, so that the compressor turbine and turbine 2 both are in the same shaft. They are synchronized to the same shaft. These two turbines are developing some total work. In that total work, some part of the work is absorbed by this compressor. The compressor is a work absorbing, because to make the compression of this inlet air, we need some energy. Okay, that energy is utilized by this the work developed by the turbine. Okay. Now, after the expansion in the first stage of first turbine, the pressure and temperature of this the working fluid is a flue gas. Here, the working fluid, it reduces the temperature and pressure. After reducing, it loses its the energy. After that, we are heating by means of supplying some of the fuel to the reheater. Reheater means it is also a combustion chamber, Only the thing is, it's having some sort of temperature and pressure. It is not completely as like as inlet air, but it is having some the temperature and pressure. Even though it's having some temperature and pressure, by supplying the extra fuel, by spraying the extra fuel to reheater, once again it is burnt and then it is again it reaches to the maximum temperature and pressure. That maximum pressure and temperature flue gases are sent to the turbine 2, so that again it is producing the same output as that of the turbine 1, as like turbine 1. Like these, the two turbines are developing the work. Total work done is calculated uh, by taking the two in by adding this work done of two turbines. Okay. Let us discuss this the TS diagram, temperature versus entropy diagram. 1 to 2 is the compression process, isentropy compression. But what is this 2 dash? It is nothing but the actual. It is the ideal one. It is the actual. 2 to 3 is the heat addition process. 2 to 3 is the heat addition in the to the combustion chamber. In actual case, we are taking from the 2 dash. 3 to 4 again the ideal work done by the stage of first stage of turbine. It is the actual one is 3 to 4 dash. 4 5 to 6 and 5 to 6 dash is the again the second stage of turbine work done. Okay. 6 1 and the 4 1. Here two cycles are there. I'll tell you 1 2 3 4 5 6 1 is the ideal, without including this 2 dash 4 dash 6 dash. If you include the 2 dash 4 dash 6 dash in the cycle, that is called as actual cycle. Ideal cycle is this one, 1 2 3 4 5 6 1. Actual cycle is 1 2 dash 3 4 dash 6 dash 1, means including losses. Excluding losses is ideal cycle, including losses is the actual cycle. The reheating cycle is shown in the previous diagram as you all discussed. Work output of the turbine operating between the two pressure limits can be increased by expanding the gases in stages and reaching reheating in between. This is done by without raising the maximum temperature in the cycle. Reheating can be done by spraying the additional fuel into the oxygen-rich exhaust gases between the two expansion states. Ideally, the reheating is done in such a way that temperature of the gases after the heat expansion is raised to the maximum cycle temperature. Number of stages is increased and the expansion process becomes nearly isothermal. Means after the expansion process, if you increase the more number of stages, here only two stages I have shown, only two stage. If you would have increased the one more stage, means the turbine HP, LP, HP, IP, LP, high pressure turbine, intermittent pressure turbine, and then low pressure turbine. If you increase one more, then it becomes HP, it is a intermittent, and then LP. And one more reheater will be there in between the IP, intermittent, and low pressure turbine, right? Like this, if you go on increasing, the exhaust will be like isothermal. If the turbine of the first stage and second stage efficiencies are equal, then T3 is equal to T5. It is called as perfect reheating. The equation becomes Pi, intermittent pressure, is equal to root of P1 P2. That is Pi by P1 is equal to P2 by Pi. Pi by P1 is equal to P2 by Pi. If you rearrange this, P square is equal to P1 by P2. Pi into Pi is equal to P1, P2. That is P square, Pi square is equal to P1, P2. That's why Pi is equal to root of P1, P2. Like this, the reheating can be done. Okay. One more important thing I'd like to highlight here. Uh, if you could have, asked the problems like this. Maybe actual cycle. Actual cycle means you will give the isentropic efficiency. Isentropic efficiency of the turbine, isentropic efficiency of the compressor. Maybe you may give the efficiency of the turbine, efficiency of the turbine of the first stage, and then isentropic efficiency of the first turbine, like that. You may give some of the superflows. Superflows means extra data also. You must be very perfect while solving the problems on these methods of improving the thermal efficiency, like the regeneration, reheating, and intercooling. In this, including actual cycle, actual efficiency, isentropic efficiency of the compressor, turbine, that equations, and this in the enthalpies, enthalpy of the compressor inlet and then outlet, and then turbine inlet, turbine outlet, second stage inlet and outlets. All these things you must know it while solving the problems. One thing I will tell you, without knowing the derivation, without knowing the notations, without knowing the proper units, and then without knowing the conversion of units, it is very difficult to solve the problems of these gas turbine cycles. Let us discuss one the very important problem. He has asked this problem in the number of times in the examination. First, a gas turbine power plant consists of the two compressors. Means here is a intercooler between the two compressors. Perfect intercooling means exhaust of the first stage compressor should be equal to the inlet of the second stage compressor. That is a perfect intercooling. The expansion occurs in the single stage, means only one turbine is there. Mass flow rate through the plant is 1 kg per minute. Calorific value of the fuel is used 42,000 kilojoules per kg. Maximum and minimum temperatures in the cycles are 900 degrees Celsius and 27 degrees Celsius respectively. The working pressure limit is 1 bar and the 6 bar respectively. The compressor have isentropic efficiency, as I said in the previous derivations. It is very important. Isentropic efficiency 80%, and then turbine efficiency is 85%. 80% of actual cycle the compressor, 85% of the turbine. The pressure ratios of both the compressor stages are equal. Determine overall efficiency, the plant, output from the plant in kilowatt, air fuel ratio, work ratio. Before going to any problem, as I said in the previous cases, you study the problem twice. And then study the problem twice means by understanding the notations and the diagrams, you study the problem, and then you go on writing the data given. That is the intercooling gas turbine. First point, intercooling gas turbine. Perfect intercooling. Mass flow rate is 1 kg per minute. CV, calorific value is 42,000 into 10 to the power 3 joules per kg, because kilo is given. The T5 is the maximum temperature, 900 plus 273, 1173 Kelvin. He has converted the inlet temperature also. Kelvin, 27 means it is a 300 Kelvin. You see here, same diagram, TS diagram. 1 to 2, it is 1 to 2 is the isentropic compression of the ideal case, it is actual case, 1 to 2 dash. And then 2 to 3 is the expansion in the intercooler. 2 to 3 is the intercooler. 3 to 4 is the ideal compression in the second stage of the compressor. 3 to 4 dash is the actual case. Actual cycle is 1, 2 dash, the 4 dash 5 6 dash 1. Ideal cycle is 1 2 3 4 5 6 and 1. Like this, ideal and actual cycle can be analyzed. Okay, P1 is the initial pressure, that is the 1 into 10 to the power 5 bar, and P P4 is 6 into 10 to the power 5. Okay, that is the bar is converted into pascals, and then compressor and efficiency is 0.8. Both the compressor's efficiency, actual efficiency, and turbine efficiency is 85, or the RPC is equal to RPC1. That is, assume, because once again I will tell you these properties of the air, that is the Cp value and gamma value. Cp by Cv is the gamma. Cp value is 1.005 kilojoules per kg Kelvin. Cv value, in case here it's a Cv is not required. In case in the problem if you required Cv value also, you should remember that is the Cv is equal to 0.718. These things may be in the data handbook but may not be in the data handbook. Okay, I think so. But you must remember this Cp value of the air, constant pressure, specific heat of constant pressure, specific heat of constant volume of the standard air, and also gamma is the ratio of specific heat, Cp by Cv. That things you must remember in the examination. Determine the overall efficiency of the cycle and work output of per kilowatt, air-fuel ratio, and the work ratio. P2 is equal to P1 by P1 by P2. That is the root of 1 into 6. It is P2 is 2.45 bar. 2.45 into 10 to the power 5 Newton per meter square. Ideal temperature outlet of the compressor, that is a T2. T2 by T1 is equal to P2 by P1 because it's a isentropic or reversible adiabatic. P2 by P1, that is the gamma minus 1 by gamma, or PC1 raised to the power of gamma minus 1, that is the T2 is equal to 387.53 Kelvin. Okay, this is yes given ratio. Okay, 1.4 also yes given, 1.4 minus 1, 1.4. Actual temperature at the outlet of the compressor 1, you know that actual temperature T2 dash. Now you have to use the actual compressor efficiency as given. Ideal one is T2 minus T1, actual one is T2 dash minus T1. He has given TC1 is 0.8, TC1, TC2. That is the compressor efficiency. Isentropic compressor efficiency of the first stage is 0.8. Again, that is also equal to the 0.8. He has given both the compressors of both the stages, the efficiency is 0.80 or the 80%. And that is the T2 is 387.53 minus 300 divided by T2 dash. You have to find this. This is the actual temperature outlet from the first stage of the turbine. That is the T2 dash is equal to 409.41 Kelvin. The inlet is 300, but it is the outlet of the first stage of the turbine is 409.141 Kelvin. Okay. Work of the compressor of the first stage is work done WC1, compressor 1, W, the suffix C1 is nothing but the work done by the work absorbed by the compressor from the first stage. It is a Cp value, constant pressure. The compression takes place at constant pressure. Okay, so that we have to consider the whatever the air which is absorbing the compressor, that is having specific heat, Cp. Cp value is 1.005 kilojoules per kg Kelvin. We have to convert that kilojoules into joules. That's why you have to multiply this by 10 to the power of 3. 10 to the power of 3 is nothing but the kilo. Okay, T2 minus T1. T2 is T2 dash minus T1. T2 dash is just how you are calculated. That is 409.41 minus 300. That is the work absorbed by the first stage of compressor is 109.9196 into 10 to the power of 3. It is a kilojoules per kg. work of the second compressor is the for the maximum work output, perfect intercooling. Perfect intercooling he has given T2 dash is equal to T4 dash. T2 dash is equal to T4 dash. And compressor efficiency of the first compressor is equal to efficiency of the second compressor. That is the N suffix C1 is equal to the N suffix C2. That is nothing but the isentropic efficiency or actual efficiency of the compressor is equal to the actual efficiency of the compressor 2, second stage of the compressor. We have T3 is equal to T4, T3 is equal to T1, it is a 300 Kelvin, T4 is equal to T2, that is the 387.53, T4 dash is equal to T2 dash, that is the 409.41 Kelvin. So that WC1 is equal to WC2, that is also equal to the 109.96 into 10 to the power of 3 joules per kg. Here, if you perfect in the theory, you know no need to write all these things. The work of the compressor 1 is equal to the work done, work absorbed by the compressor 2 is more than sufficient. That is the work of the NC or WC1 is equal to WC2 is equal to 109. If you write that step also, that is a more than sufficient. Okay, no need to write all these steps. Okay, here only for the explanation sake, I have written the elaborate steps for you. Next is ideal temperature of the turbine outlet T6. T6. T5 by T6 is equal to RP gamma minus 1 by gamma. T6 is equal to T5 by RP. The pressure ratio, maximum pressure is 6. 6 by 1 is the maximum pressure by minimum pressure is 6 by 1. Again, if you divide anything with a unit quantity, there is no change in the value. That's why it is equal to the 6 only. 6 to the power of 1.4 minus 1 divided by 1.4. It is the T6 is 703.4 Kelvin. Actual temperature at the turbine outlet T6 dash. For T6 dash, we need the isentropic efficiency of the turbine. Isentropic efficiency is T5 minus T6 dash. But here you must be very, very careful while calculating the isentropic efficiency of the compressor, isentropic efficiency of the turbine. Here actual we are taking in the numerator. In the compressor, actual we are taking in the denominator. Okay. If at all, if you go to the previous slides, you can observe here. T2 minus T1, it is ideal one. T dash is coming in the denominator. But here in the turbine, you are getting the dash, T6 dash, it is actual case. T6 dash in the numerator. But in the compressor, it is coming in the denominator. That you must be very, very careful. If you take the wrong equation, if you substitute the wrong things here, your problem is going to, the answers are going to wrong, concept is going to wrong, and finally you will not be awarded any marks, because this is the important fundamental concept in the gas turbine. But you are not applied that concept to the problem solving purpose, then the examiners are going to assume that you are not aware of this the concepts. That is the isentropic efficiency concept, actual cycle, ideal cycle concept. Okay. T6 dash is equal to 773.53 Kelvin. Turbine work is equal to, again, it is the isentropic expansion, that is a constant pressure process, constant pressure, the expansion takes place. That's why here we are taking CP of the exhaust gas. Here some cases the CP of the flue gases is going to mention in the examination, in the statement of the problem. At that time, CP of the air you should not take in the turbine work calculation, right? At the time, CP of the exhaust gases, if you mention, you have to take that. Otherwise, he has not given, you can take your own value, that is the standard value of the air. Standard value of the air, that is CP of the air is nothing but as I said, 1.005 kilojoules per kg Kelvin. That you take 1.005 into 10 to the power of 3 only, you must substitute, because it is in the Kelvin, because all the substitution should be in the same unit. Then only you'll get some sort of the value. Otherwise, value may differs. Net work done. Net work done is nothing but the WT minus WC. WT is only one turbine is there. WC is see here 109 is added. It becomes a WC is equal to the total of two compressors. Work absorption by the compressor is nothing but the work absorbed by the first stage of the compressor plus work absorbed by the second stage of the compressor. That becomes the total absorption of the compressor. Total turbine work developed by the turbine minus of the work absorbed by the compressor gives the net work output. Okay, net work output, that is 181.55 kilojoules per kg. Joules per kg you'll get. Heat supplied is Q supply Q4 minus Q1 Cp T5 T3 minus T4 dash, it is 1.005 10 to the power of 3. This heat supply have explained in the earlier sessions very clearly. Overall efficiency also it is same overall efficiency, and then our output of the plant is kilowatts. That is nothing but the mass also he has given. That is the 1 kg per minute he has given. But you have to supply for the kilowatt is nothing but the kilojoules per second. But mass you are substituting in the kg per minute. So that if you want to get the in kilowatt, you must substitute this mass flow rate in terms of kg per second only. So that what you have to do for 1 hour, the 1 minute, kg per minute, 1 minute, there will be the 60 seconds. So that 1 by 60. 1 divided by 1 minute is divided by 60 seconds, and hence mass flow rate becomes a kg per second into the net work output, that is the 181.55. It is again in kilojoules per second only you are substituting, so that you will get the 3.03 kilowatt. Watt is nothing but the joules per second. In the previous case, kilojoules per kg you are substituting. You are getting this, but here kilojoules per second, that is nothing but the kilowatt. Air fuel ratio. We know that heat supply by the fuel is Q supply is given by Q supply MF into CV. MF is the mass of the fuel supply into CV. MF into CV, you will get the heat supply you are calculated. MF you have to calculate mass of the fuel into CV is 42,000 kilojoules per kg. You must convert that into joules per kg. That's why you are substituting this 10 to the power of 3. Mass of the fuel supply is 0.0183 kgs per second. Kg per second mass will be supplied to develop this much of power. 3.3 kilowatt of power will be developed. 3.3 kilowatt of power will be developing by supplying the 0.0183 kgs of fuel. That is the meaning of this. Air fuel ratio is 1 by 1.083. That is the 54.83 is to 1. 54.83 air fuel ratio. Okay. Work ratio. Work ratio is that is the net work output divided by turbine work. Net work output is the after absorbing the compressor, whatever the work is going out from the turbine is called as a net work output. But turbine work is again it is a total work developed by the turbine. 181 divided by 401, you will get the 0.45222 work ratio. Thank you.